Okay, so this is the revision PowerPoint for topic 2, which is electricity. We'll do it in 2 parts. If you remember, we started off by pretending to be an electrical circuit. Remember, we walked around the lab carrying little pieces of paper. Remember, you represented the electrons in the circuit. Yeah? So you collected a piece of paper from the cell. If you remember, this was me. You went to the lamp, which in the lab was a Bunsen burner. You burnt your piece of paper and you returned to the cell. So the pieces of paper represented the energy in the circuit. So basically the electrons carry energy from the cell to the lamp and then return to get more energy. Okay, so if you remember, electrons are incredibly small. They're the smallest particle we'll think of. They're 0.3001 kilograms, so they're incredibly small. And literally trillions of them go around a circuit every second. So it's easier for us to think of a quantity of electrons called a Coulomb. A Coulomb of electrons or a Coulomb of charge. Now you don't need to remember this number, you just need to know that when we talk about a Coulomb of charge or a Coulomb of electrons, it's a very, very big number. So when we measure the current in a circuit, we're just measuring the number of coulombs that go past every second. And if 1 Coulomb goes round every second, we call that an amp. We say that the current is 1 amp. So if you look at the bottom right-hand corner here, 1 amp is 1 Coulomb per second. And to count that, we have to put an ammeter in the circuit, sort of in series with the circuit. So the electrons actually go through the ammeter. Okay, when we measure the voltage, we're measuring the difference in energy between the electrons when they go into something and when they come out. And so we're measuring how much energy each Coulomb is carrying. And if each Coulomb is carrying 1 joule, so there's 1 joule per Coulomb, we call that a volt. Now, when we measure the difference in energy across a cell, that voltage we actually call the EMF. Notice the voltmeter is connected across the cell. Yeah, it checks how much energy the electrons have got when they're going in and how much when they're going out. Okay, so the voltage across the cell we call the EMF. If we connect the voltage across a lamp, so this time we're measuring the amount of the energy the electrons are giving, we call this the potential difference, the PD, but it's also measured in volts. So remember, the volts measures how many joules per Coulomb the electrons receive from the cell, and that voltage we call the EMF, or how many joules per Coulomb the electrons give to the cell. Remember, we call that the PD. If you remember when we did this in class, I gave you a draw the sentence exercise. Yeah, so this really describes what happens to electricity. Electricity is the flow of electrons. We measure electrons in a quantity called coulombs. 1 amp means 1 Coulomb of electrons flows around every second. The electrons carry energy from the cell to the lamp. The electrons then return to the cell to get more energy. So the electrons are not used by the lamp. Voltage measures the amount of energy each Coulomb receives or gives. Okay, so that's pretty much electricity, really. Okay, we looked at symbols. Now, I'm not going to go through all these. You just need to know these. So I'll go through them very quickly. Cell and battery of cells. Notice they're all connected the same way around. The long line is the positive side. Yeah, the short line is the negative side. Okay, this is the power supply, so the things that we use in the lab when we're building circuits. This is a direct current power supply, so it's the positive side and the negative side. This is an alternating current power supply. We've not really used alternating current in the lab yet. A lamp, you know that one. An open switch, obviously a closed switch, which is like a closed door. If the switch is closed, then electricity can flow. Ammeter, voltmeter, resistor. Variable resistor, that is sometimes called a rheostat, a variable resistor, a resistance whose changes. Okay, a fuse, we'll talk about fuses more later on. Okay, a bell or a buzzer. Okay, now these ones are a little bit more complicated and you need to know a little bit more about this. So this is the thermistor. As the name suggests, the resistance changes with temperature. And you've got to remember when the temperature is low, so when it's cold, it has a high resistance. When the temperature is high, it has a low resistance. What happens is the thermal energy releases the electrons in the resistor, so it's easier for it to conduct electricity. A light-dependent resistor, Okay, so you imagine these arrows represent the light. And as this suggests, the resistance depends whether you shine light on it. And you're going to have to remember this, that when it's in the dark, when there's no light shining, it has a high resistance. When you shine light on it, the resistance gets lower. You need to know that. Okay, a diode, if you do A-level physics, I might teach you how these work. But a diode just allows the current to go through one direction. So the current can go from positive direction in that direction, but not in that direction. So if you look in the direction of the arrow, that's the direction that the conventional current can flow. The conventional current cannot flow in the opposite direction. Okay, so just let's have a look at the current a bit more. So just a reminder, we have this quantity of electrons called a Coulomb, and the current measures the number of coulombs per second, and we call that an amp. So we did some experiments, we measured current in circuits, and we discovered that in a series circuit, remember that's where the electrons have no choice, the current is the same in all parts of the circuit. And if you think about it, that has to be true. The electrons are not used by the lamps, so the current going into a lamp must be equal to the current going out. Conversely, in a parallel circuit, the current splits. The electrons come out, so let's say 2.5 coulombs per second, half go that way, half go that way, if the lamps are identical. Okay, so the current in a series circuit is the same, the current in a parallel circuit splits. Okay, and this formula, if we know the charge in coulombs and we know the time in seconds, we can calculate the current as the charge divided by the time, the number of coulombs that flow per second. This symbol I we use to represent current in equations. A little bit confusing, but there you are. I think it's because current used to be called intensity. Okay. We then looked at voltage. So don't forget, voltage measures the amount of energy per coulomb of charge that each coulomb receives, or each coulomb gives. If we're measuring the voltage across a cell, we call it the EMF. If we're measuring the voltage to a clamp, we call it PD. We did some experiments, we discovered that the opposite is true. So in a series circuit, the voltage splits. And if you think about it, that makes sense. The electrons receive 9 joules of energy per coulomb. They give 3 to this one, 3 to this one, 3 to this one, so the energy is shared. A little bit harder to understand, but in a parallel circuit, the voltage is the same across each component. Because let's imagine one electron comes out with these 5 pieces of energy. Well, he can only go one way. So if he goes this way, he gives all of his energy to this lamp and goes back to get more. Okay. If another electron comes out with their 5 joules of energy and go this way, they give all of their energy to them. So remember, the voltage measures the amount of energy that each coulomb gives. So in this case, they're the same. Okay, so that's the end of the first part. In the second part, we'll go on to look at resistance and power.